Hola everybody, good morning. So one of the things that we have learned about integrals is that they can be used to go back on a function to find the antiderivative of a function. Well, another property that we can use for integrals is to find the area. I want us to learn a little bit about the theory behind the method used to calculate this area. And somebody who influenced a lot in this theory was Archimedes. Archimedes was this greatest, quote unquote, applied mathematician that he lived from 287 to 212 BC. Or from 212 to 27. One of the two. All right. But he used the method of exhaustion. What is the method of exhaustion? Well, back in his day, people and mathematicians were wondering about how to calculate the area of a circle. And nobody knew any formulas to calculate the area of a circle. So Archimedes was like, I show you. Why don't we take a circle, and then on the circle we draw a square on the outside that is circumscribed on the circle. That means around the circle, outside of the circle. And we calculate that area, and that area will be the area of this whole squared. And then he said, well, not only that, well, what if we calculate the area of a square that is inside the circle? It would look something like this. Da, 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 da. And if we calculate the area of this, we notice that the area of the small square is less than the actual area, and the actual area is less than the area of the big square. That is the reason. He said, well, now if we let this square become a pentagon, a hexagon, a heptagon, an octagon, nonagon, and decagon, and I don't know what's after decagon. And we let it go all the way to any big number. How would this look like? Well, it will look something like this if we start increasing to any n number, and eventually we end up that the area of the inner polygon is very, very close to the actual area of the circle, and the area of the circle is very, very, very close to the area estimated from the polygon outside of the circle. So this was the method of exhaustion. Exhaust all the sides of any polygon, and then you get a nice approximation for the area of a circle. So this is a nice little fun fact to remember, that the sum of all interior angles in any n-gon is given by s is equal to n minus 2 times 180, and n is the number of sides. And this has to do, and this makes a lot of sense, because here, if I give you this figure, we can always create one triangle, two triangles, three triangles. So we have what, 5 sides, we have 3 triangles, and each triangle has 180 degrees. If we create something that has only 3 sides, there you go, right? 3 sides, how many triangles? 1 triangle, 180 degrees. What if my polygon has 1, 2, 3, 4, 5, 6? All right, well, we can create 1 triangle, 2 triangles, 3 triangles, 1, 2, 3, and 4 triangles. So if we have 6 sides, we can create 4 triangles, and each triangle is 180 degrees. So for any n sides, we get n minus 2 triangles times 180 degrees. This is a formula to calculate all the interior angles of a polygon. Well, the question for you is, how about the sum of all the exterior angles? Come on, think. Alrighty, well, that was Archimedes. And now the question is, if we move away from just a circle into any shape, any plane region on the coordinate plane, how do we find the area of this plane region? And do we split it into shapes? And if so, what shapes do we split it into? And also, where do we make our starting point of all our shapes, right? Do we do something like this, and this is a triangle now? And then this is a triangle, or should we have chosen this part right here, and now this is my triangle, and this is my triangle, and another triangle, and so on? Or what if we just focus on the first quadrant? What if I just want this region right here? If I want to calculate the area, how would you suggest, what shape do you suggest inscribing in there to be able to find the area? Well, the problem with that is that we don't know where to start or what shape to use. We have so many options, and to solve this, they said, well, hold on one second, what if we standardize this, right? Everything seems to be about standardization. So what if we draw a rectangle, and moreover, not just a rectangle anywhere, actually a rectangle inside the figure? And how many rectangles? Not only 1, 2, 3, 4, 5, 6, but infinitely many rectangles. So if we draw a rectangle So if we draw a rectangle here, right, I can calculate that area. I know the formula for a rectangle. I know the formula for this rectangle. I know how to calculate the area of this triangle. I know how to calculate the area of this triangle, and this triangle, and this triangle, and this triangle. All right. So if rectangles. Another problem becomes these rectangles. You see, that's the problem about humans. If you give them more options, then the less decisive they become. All right, so not only can we draw a rectangle like that, but let's see, just even a rectangle, how you draw it can look different. For example, if I have this interval inside my space where I want to draw a rectangle, this is how I draw my rectangles. Usually I go up all the way to where it's supposed to be, and I go over just a tiny bit. And I go up again, and I go over just a tiny bit. Same thing. I go up, I go over just a tiny bit, I go over just a tiny bit. What just a tiny bit? Because we're going to learn how to draw a left endpoint and right endpoint. All right, how does it look from the left endpoint? Well, you pretty much look at your left endpoint. Just follow that one, left, 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 left. Whatever it touches the graph, that's where I draw my line towards the other endpoint. Ta-da! That's a rectangle, right? Using that left endpoint. Well, on the same figure, what if we use the right endpoint? Well, let me pick the right endpoint of my interval. And let me follow the right endpoint all the way up until it crosses the graph a little bit. There you go. And then just make a line from where it touches the graph all the way to the other endpoint. And that's how we do it. Ta-da! So now this is the rectangle that I can approximate area for, or this is the rectangle that I can approximate the area for. And if you can observe, if I use this type of rectangles, I will get an underestimate, but if I use this type of rectangles, I will get an overestimate. And that is what we refer to as an upper sum or a lower sum of a plane region. But for our purposes, we're going to be referring to as the left endpoint or the right endpoint. Why do I do that? Because it's easier for you to first decide if it's going to be a left endpoint or a right endpoint, and then based on that drawing that you get, that's how you determine if it was an overestimate or an upper sum, or an underestimate or a lower sum. This is some of the possible ways to calculate the area. We can divide into triangles that are actually an underestimate, and this will be a lower sum, and we're going from A all the way to B on the X coordinate and on the Y's. All right, and we can also draw rectangles that are over, and this will be an overestimate. Or we can say, well, hold on a second, let's not go all the way to the right or to the left, let's stay a little bit in the center. Let's call it the midpoint. Well, if you use the midpoint of any rectangle, you can also get an estimate of the area for that. But for now, in our purposes, we're going to be using the left endpoint and the right endpoint to approximate areas.